for implementation of new methods. And additional, my motivation, if some of you who really like experimental work, who are very close to hardware type of thinking, will find it extremely attractive. Yes, and maybe some of you will be involved in this area, because again, it's a very promising growing area, especially now with those new techniques. And again, you can relax today probably during the lecture, because I will show you just examples, a lot of images, a lot of graphics here. There is no correlations with your homeworks, but again, I would be happy if at least some of you connect your future with, at least partially, with experimental methods. Yes. So again, examples of experimental characterization, and we have quite intensive program today to cover. Yes, we will cover several advanced methods. Yes, one of them is digital image correlation. It's one of my favorite, actually. And another application of computed tomography. Again, each of them could be maybe a special course, including practical exercises in the lab. But at least I want to be sure, within our high-level course on aerospace materials, you're familiar with them, and you would know when to use if needed. Yes. And also we will go through several, as you see, specific examples. Yes, stiffness characterization, strength characterization, example C, interlaminar toughness characterization, progressive damage, and in situ characterization using full-scale structures. And again, I'm giving just examples, because it could be maybe dozens and dozens of those, maybe even hundreds of those, but just as a representative, so you will see the beauty of experimental approaches and how to connect them with computational methods, yes, or analytical methods, yes. And I consider myself more like analytical / computational, but I really enjoying experimental part, and I was lucky to always collaborate with people who are, born to be experimentalists, yes. So this is the best scenario when you have team, analytical people, experimental people, and you work together, supporting each other, yes, and creating really results with high level of confidence and practical impact, yes. And one additional comment here, I'm showing examples from papers we published already, so they're publicly available. So if you have any, so there is no restrictions to share. So if some of you have specific interest, just drop me an email, yes, and I will send you actual details. Yes, so there is no restrictions regarding those examples, because they were already published. Yes, and of course there are, you can imagine, much more what we are doing internally. Yes, but it's usually confidential and proprietary. But those results can be captured and captured for public distribution. Yes, used for public distribution. Sorry. So let's start with digital image correlation. Yes, and let me show you high level picture how it works. It's extremely promising experimental methods, and it could not be done like 50 years ago, because it's based on advancements of computational progress. Yes, and how it looks like. So you see my cursor. So imagine you have a surface of a structure. Yes, a surface of a coupon you want to analyze. Yes. So on the surface of this structure, you could put a couple of points, not a couple, actually, in reality, it will be thousand and thousand, but for simplicity, I'm kind of describing as a several points. For example, with, pen or pencil, whenever, yes, we're not talking about methods how to apply them. And actually, there is even sub-industry how to make those, points efficiently. Usually those point code speckles, but bottom line, if you have surface and you have several points here, yes, they're fixed with surface, yes. So now after that, if you apply some load, so your structure start to deform, as shown here, the right image, definitely, your structure will deform, but also all those speckles point here also will be deformed, yes. So we moved from this position, for example, this guy, yes, will move from this position to that position, yes. And another point, for example, point here, will move from this position to that position, yes, and so on and so on, yes. So if we have just, 3 points here, so what we can do, we can manually, again, or under microscope or whenever, but theoretically, we can measure displacement, how each point is moving, yes? So if I down select this point, and I know its original position was here, and after deformation, it's somewhere here, I could say, I can potentially measure this displacement and that displacement, yes? So again, it's a very simple kind of logical concept, but it's not easy, of course, to do it in real life experimentally because for our structures, we have relatively small displacements, so it's required high-level accuracy of monitoring, and I will speak about it, but it's possible to do in principle, yes? So now imagine if instead of 3 points, you have really, thousands of points. Or in real life, actually, we're talking about tens or hundreds of thousands of those points. So if for all of them, we can measure those displacements, yes. So eventually what we received a field of displacement in one orientation and field of displacements in another orientation, yes. And if we correlate it with initial position, X and Y, we can actually create this surface, for example, here, function of displacement UX as a function of coordinate X and Y. And similar, we can create displacement in orientation Y, yes? Theoretically, yes? So now, if we have this huge population of displacement as a function of X and Y, we can approximate them with analytical function, for example, in form of spline or Fourier series. And after that, calculate strains. And strain can be calculated as a derivative of corresponding displacements. And here I showed you just strain in orientation XX. It will be derivative with respect to X. If we want strain sub Y, it will be similar displacement in the orientation Y differentiated by dy, and similar with shear. Yes, in shear, we need to consider both components, as you know from classical strength of materials or classical theory of elasticity. So again, concept is the following. Initially, we provide several points, what we call speckles at the surface. We monitor their movement under different type of loads. After that, we characterize those field of displacement with numerical or analytical surface function. And after that, we can do analytical derivation and calculate strains. Yeah, so relatively kind of, 4 key steps. And here is example, represent example how it was done in real life. So for example, you have coupon, it looks gray, but actually it's not gray. Actually, it's black with white speckles. Yes, there is special techniques how to apply those speckles. And usually if surface is black, speckles will be white. And if it's like white or very light, speckles will be black or dark at least. Yes, kind of to have as much contrast we have, the better. Yes. So this is the reason it looks like gray, but in reality, here you have, really tens of thousands of white speckles at the surface. Yes. So now what you see here, it's usually there is high precision camera, zoom camera, but is able not only to capture all of them speckles, but based on developed software, correlate each initial points with corresponding displacement. Yes, so there are kind of two very important component in practical implementation. One is you need to have really good optics, yes, sometimes modification, and another is very good software to be sure the program will capture initial position, and every time you apply load, yes, it could capture new position and quantify it. So now you see, this technique can be used for tons of scenarios, yes? And I will show you a simple case. So for example, if I have from one of our works, when we were trying to analyze process of damage of interface between one composite part and another part, yes? It's like two pieces coupon, interface under angle alpha, we apply tension load, and what you see here, this is actual photo of this coupon, yes? And this white, it's interface between them, representing adhesion, yes, or glue between them. This is scenario there again, actual photo, when after critical level of load, it will be damaged, and now eventually we'll have two pieces. And this is actually how we can see through, this damage image correlation technique, intermediate step of loading. When you apply tension, here you see strains are more or less uniform, green. Here strains are more or less uniform, green. It's somewhere in this domain, but interface heavily deformed, yes? And this is calculated strains, yes, through this thickness, what the program automatically generates. The program automatically generates based on, direct measurement of field at different step of logic. This was definitely, maybe easiest scenario, not as easy, but kind of from geometrical perspective, because we have flat coupon, nothing is complex, but now those are couple of examples from more complex real structures. When we have non-flat, you see curvature here, here it's connection between one shell to another shell, and this is one example, yes. On the top, we see measured displacement field. And because we have so many points, really tens of thousands, maybe hundreds of thousands, the field became extremely smooth, very nice, a kind of non-uniform distribution of measured displacement. And this is side, what you see at the right side, it's analytical calculation of strain as analytical derivative of displacement measurement here and calculate here the strains, yes? And of course, you see strain concentration will be somewhere here. And if you will designer say, aha, this is what I need to worry, have to, check if it's strong enough. And if yes, keep it, or reduce thickness, reduce sizes, and vice versa. If it's not strong enough, you will need to change size or change geometry. Yes, change geometry. And this is another example from similar structure but different position. Again, you see we have curvature in one orientation, curvature in another orientation. Two surfaces contact each other under certain angle, and those are measured displacement in orientation X, in global orientation X, yes? And here it's already calculated distribution of strains based on measurement of displacement and follow-up derivation, yes, derivatives here. And again, this paper was focused on how to make analytical calculation of strain much more robust. So actually our approach was, don't want to spend now time, but kind of to emphasize to be sure strain distribution is very smooth, yes, and capture into account randomness and imperfection of measurements, yes. So actually, eventually we got very smooth distribution of strain, even better than we have here. But bottom line, even with this relatively coarse assessment, I can't say coarse, but maybe, with some level of random variation, uncertain variation, we can still easily see maximum strengths here and another extreme here. Blue would be negative and red would be positive, similar as here, yes? So this is a concept of digital image correlation, extremely powerful method of experimental analysis. And practically in all examples which I will show you today, we will have kind of, usage of this technique, and you will see how it's wonderful for not only validation of your prediction, but also understanding of what is going on in reality, yes? And one maybe additional comment here, this technique can be applied not only for static load, but could be applied for any other scenarios. It could be applied for thermal deformations. We applied it, for example, when you apply heat, so its structures start to expand or shrink if it's negative temperature because of coefficient of thermal expansion. And if you have different materials together, of course, it will be a redistribution of thermal stresses and strains, yes? So to capture thermal strains, DIC, it's extremely powerful methods. It's very good for fatigue analysis when you have cyclic load. It's very good for high-speed load when you have impact or ballistic or crash type of analysis. In this situation, you just need to use high-speed cameras, yes? And we also applied for many dynamic problems, including crash and vibration. Yes, so, there is no limit. And, again, strongly encourage some of you who will move to experimental worlds to pay attention and maybe to be involved with this technique. Any questions, comments so far? No, so let's go to our another example, and now let's go to stiffness characterization. And again, I will use example of off-axial tension, and you will see even this relatively simple test can be extremely powerful from the viewpoint of generating new results. Yes. Let's go. So paper was published when some time ago with my co-author Pat Clavet, and this is a statement of the problem. Yes, so you remember when we discussed last lecture, at least you can remember, I mentioned that it's extremely powerful test when we have coupon of composite material. Coupon of composite material cut under different angles. Yes, so this is a scenario. We have rectangular coupon of composite material. Material orientation 1 is under angle alpha. Under angle alpha with applied load. Let's code it 1 prime. And in your kind of lectures, we usually code it X, but it's practically the same. So because material orientations not correlate, it's not the same as orientation of applied load. When we apply tension, as we know, yes, because under angle, it will be shear, non-zero shear, yes, so it's elongate, but also will be non-zero shear, as we discussed in our homework 1, for example, yes? But let's prove it. Let's prove it's experimental. So, for example, here, we have this diagram is, you see it's excuse me, it's strains in orientation 2, yes, 2 prime, and this is a strain in orientation 1 prime. So again, because of material orientation under angle, you see distribution of strain is under different, sorry, not the strain displacements, yes, it's under angle, yes. So this is kind of experimental proof of our analytical expectation. It will be what? It will be shear here, yes. And in orientation 1, of course, we have much bigger displacement, but we still have also displacement orientation 2. Why? Because of Poisson's effects, yes. So here you see there is a shrinking in this orientation, shrinking in this orientation, yes. But again, it's an excellent example of experimental observation that if material orientation does not correlate with load direction, yes, we will see some additional shear effects. So I'll skip all math that we, presented here. And here we'll show you what was done. Those images are already shared with you as example DIC, but we created, you see, different coupons, representative coupons under different angles of fibers, yes, under different angles of fibers. And please pay attention, at ends, we have those kind of clumping devices. You need to glue them to be sure when you clamp them and apply a load, composite part will not slip, yes. Again, we discussed it at our last lecture, but this is just, a good example how those actual coupons are done, yes. And now a couple of examples. For example, I'll select coupon under angle 45 degree, 45, it's in this orientation, so sorry, in this orientation, because, and now I'm playing with different level of load. At the very beginning, yes, there is no load, so displacement are uniform. Red is 0, no displacement. I increase level of load, so it became slightly non-uniform, yes. At one side, there is no displacement, and it started to move opposite side. So we fixed here and applied load here, yes. You see my hand, yes, from the bottom. Now I increase level of load for 50, 900, 1350, 1800, 2250, and you see non-uniformity increase, and the higher level of displacement we have, the more obvious we see this kind of shear, yes, because of this angle 45 degree, yes, and all of them have, of course, some level of non-uniformity, but with higher load, of course, it's much easier to see, yes, and this angle actually is represent this shear, what we would expect for this type of position. And very important to emphasize, like for this type of problem, yes, if material properties would be the same in orientation 1 and 2, we would not see this shear, yes, because it will kind of deform uniformly, yes, as we discussed in modeling of deformation of anisotropic bodies, yes. And this is another interesting example. Now, if we can play with the different angles, yes, coupons under 0, 15 degrees, 30, 45, 60, 75, 90. This is 90, what I discussed just, it's actually material orientation perpendicular to load orientation. So when you apply load, all of them move parallel, yes, so there is no shear. Similar scenario with 0, it's practically parallel. But now if we consider different angles, yes, this kind of shear became more and more pronounced, of course, with higher angle. So you see at 15 degree, we have higher angle, with 30 degree, we have this angle, 45, 60, and 75, it's close to 90. It's not 100% uniform, but this angle here, it's relatively small, yes? So again, it's perfect example of experimental validation of expected analytical trend with respect to shear, but of course we had tons of additional data, have to analyze them. And actually what we did here, we use those results to understand what is variability of stiffness properties, how much we can trust them, yes, how much we have plus, minus. Ladies and gentlemen, any comments, questions regarding this example? Yes. So let me go to the next example. It's strength characterization, yes. And again, it was published with my co-authors, Mark and Patrick, in 2016, so I can share with you. And here interest was to characterize interlaminar strength. You remember from, or may remember, hopefully, from our lectures that, for composite material, interlaminar strength is actually one of the most important allowables, because interlaminar behavior is the weakest usually. In plane, we have strong fibers, but between layers, yes, only polymer, yes. So usually it's a big problem to be captured, yes. And for example, here at the left, I showed a couple of photos when we have ply ends. And, here you see boundaries interfaces between different layers. So when we apply load, for example, bending or other, or twisting, usually fracture pattern, something like that, crack initiated at interface and quickly propagate, yes? So to capture that and to analyze, we need to know allowables, yes? And this scenario, it's very typical. I'm showing here one of representative example. It's actual rotorcraft component here. Sorry, yes. Actual rotorcraft component here. So those interlaminar type of damages could be in one orientation, XZ, could be another orientation, YX, here at the very end, here inside, but this is quite typical type of scenarios, yes? So to characterize it, we need to have, let me go here, this interlaminar shear strength. So what to do, and actually traditional test, it's something like that. 3-point bending, you have two supports, you have impactor where you apply load, and because of this bending, yes, here you would expect shear, yes, shear component through thickness, but eventually break it if it's relatively short, But we moved, beyond that. We could say, okay, let's check if the same properties will be under different load conditions. So this is scenario when you can kind of squeeze both sides to have built in, but still use the same 3-point bending, but under different load conditions. But here we propose 5-point bending, 5-point point test, yes. And here, similar scenario, but with different aspect ratio. Reason why? Because 3-point bending is statically determined. When damage happens, the structure is practically gone. But with the statically indeterminate system, like here, you have force damage, the structure still can handle load. You increase the load, it will be next damage. So it was extremely powerful test what we proposed to analyze progressive damage. Yes, progressive damage. But here, let's speak about interlaminar shear. Those are finite element predictions for half of them. So for example, if I have this half, this will be one support, another support, the impactor. So maximum shear stress are expected here and here, yes. If I have similar 5-point bending, yes, maximum will be somewhere here. And if I have 3-point bending, for a half, maximum shear component will be somewhere here. So those are predictions, 100% computational, no experimental. And after that, I will show you how we can measure them and prove it, yes? So those are, actual test for 3-point bending, 5-point bending, and 5-point bending with, long span between supports. And this is what usually people report upon testing. This is force. This is displacement, similar to we discussed. At the very beginning, go from zero, linear, boom, it will be damage, go down. Yes, after that you continue increase load, boom, it will be second damage. Again, stiffness go down, you continue, boom, boom, boom. Sorry. So it's extremely, interesting way to capture progressive damage. Yes, but again, from the viewpoint of interlaminar shear strength, major interest in this point. And why you see here two lines? Because I just showed two different coupons, because no two or three different coupons will show you exactly the same. It will be some level of variation, but they're still relatively close, yes? And this variation actually one of critical output of experimental test, yes? Now, if we have 5-point bending, again, it's similar scenario. Here you have force, here displacement, you increase load, go from zero, almost linearly, boom, 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 up to this point, boom, force damage, yes? Stiffness dramatically go down, you continue increase, after second damage, again down, 40, boom, 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 continue to go, eventually completely collapsed, yes? And for 5-point bending, again, it's similar approach. From zero, go linear kind of deformation up to force damage, go down, etc. And what is important, here we had displacement control test, yes? So what we are doing, we gradually increase displacement. In other words, vertical movement down on this guy. And this is the reason we can capture all future steps. If it would be force increase, we would generate just point diagram up to this point to increase force, because you cannot increase after that. Here would be end of the test. But with displacement control, you continue up to here, go back, and so on. Yes. And again, each of them are shown with two coupons. Usually we have at least 5 coupons, different coupons per test, to generate relatively, good, statistics. But as you see here, here, and here, all of them are relatively close. So it's provide very good confidence. Yes. And now this is example of DIC-based, measurement of strain, shear strain, yes. So you see this diagram, it's shown just before damage. Definitely here we would expect maximum strains. Here I applied a little bit more load, and boom, here will be interlaminar crack, but captured experimentally, And again, this is 100% experimental mesh distribution, yes. And this was, if you remember what I showed, this was what I expected analytically. So almost like twins, yes. So it shows us that we can really trust generated results. Actually, it was for this, sorry, it was for this one. So we can trust the generated results, not only at absolute level, but its point, but also as a distribution of one field versus another. Yes. And this is, let me make a little bit bigger here. This is process of multi-step damage, progressive damage. So, this is support and center. Those are left, right, and two impactor on the top. 5-point bending at the very beginning, no load. You see A load 0, there is no damages. So increase level of load, for example, 19%, 19.5%, boom. I will see the first crack here, first interlaminar crack. Let me make it a little bit bigger so you can see it. Probably you can see this crack, yes, here. Continue increase load, here will be the second crack. Continue increase load, it will be the fourth crack. So continue with the load increase, it will be more damage, and eventually it look like that. Scenario, it's still capable to handle load, but now we see a lot of interlaminar damages, yes? And actually they can be predicted by damage tolerance criteria. It's another kind of set of papers we published have to correlate this experimental process of damage versus analytically predicted. Yes. And eventually, let me go back. Yes. Eventually, it will look like this. Yes, it's a photo when we have all those interlaminar damage at extreme level. And those photos, now you see photos of tested coupons. After that, you still see after the test those interlaminar damage. And this is exactly what we wanted, to create like standard test to capture interlaminar damage progress. Yes, because it's one of the critical weakness of laminated structures made of laminated composites. Yes. Any questions, comments so far? Again, just for kind of your illustration, but wanted to be sure, you see it's has a real kind of practical importance. So next example, interlaminar toughness. Yes, interlaminar toughness. Have to characterize it. And again, published a paper here in this area. It's called with focus on probabilistic characterization of interlaminar toughness. Yes, I'll skip probabilistic portion. I just will show you interlaminar portion, but it will be easy for you to see how actual test is performed, done. Yes, skip it here. Yeah, so we started with this example from previous paper, and so okay, to predict this process, we need to know damage tolerance properties here, primarily toughness. Yes, not only strength we discussed in previous paper, but toughness. Yes, in other words, if you have already crack, what is the risk this crack start to propagate? Yes, so what we used, let me skip it quickly. We used this test as we discussed. This is standard test recommended by community. You remember I mentioned in previous lecture STM standard. So this is one of standards. So how it looks like, you have relatively short composite beam, here are layers, and here you artificially introduce crack, for example, by Teflon insert, or just having zero bonding between top and bottom part. Yes. So now you apply a load to mimic 3-point bending. So here will be shear component, as we know. So sooner or later, this crack start to propagate. Yes. And this is a test to capture moment of damage growth. Yes. And the damage growth will be eventually quantified by toughness characteristics. Yes. So this schematic representation, we discussed it in previous lecture, but I just wanted to show. And this is how it's actually look like. Yes. Photo have one support, another support. You have impactor when you apply load. Why it's white? Yes. It's white because we cover it for DIC. Yeah? So we covered it with white speckles to monitor also field of strains. And this was our tip of our crack. But what we proposed, we could say, okay, if we are interested in variability, statistical variability, let's check how repeatable our data are. Yes. So instead of making this coupon, we proposed very long coupon. You see it point A. So when we have supports here, and here, an initial crack here, it's practically the same test. But our approach was, let's apply a load. Let's see when cracks start to propagate. You see, this is black is our original introduced Teflon crack, and red is propagation. After that, stop test and move it. Yes. So move supports here and here and repeat. So now crack start propagate from here. After that, from here and so on. So if you have relatively long coupon, from one coupon, actually, you can capture a toughness measurement several times. And actually, in our examples, we capture up to maybe sometimes 20 times between, 15 and 20 times, many of them. Each data here will be slightly different through statistical variation, but altogether it will give us very good statistical pool, yes, providing high level of confidence. Yeah, so this was approach what we did here. But again, to emphasize, this is a very practical test what people are using. Yes, let me skip it. So, for example, this is example crack number like 1, 2, 3 with each implementation. You see almost up to 16 or 70. So from one coupon, many data point can be generated. But what we saw actually, big difference between initial crack, yes, and initial crack is defined by Teflon insert and relatively smooth end versus a natural crack, what we called them, yes. And difference was almost, or twice, yes. So it was one big observation, and another was that there is a relatively significant statistical variation defined by this cloud and by this cloud, yes? And we played with different coupons of different thickness, and actually we saw if it's thicker or thinner, generated data could be also slightly different, which was important for our application. And this is kind of probabilistic distribution. Let me skip it. Similar for 30 layers, and this is similar for 40 layers, yes. Here distributions, and eventually you see this kind of green line, it's cumulative probability function. So it could have relatively big variation from 2.5 up to almost 4.4, yes, big variation. Again, I don't know how much you are involved in theory of probability and statistical analysis. You mentioned some of you had measurement classes. So, eventually data can be summarized in form of histogram. So this is what we did. And based on those histograms, we could say, aha, we are able to select not only average value, but also, tails, like the worst case scenario with given probability. So actually what we did here, calculated statistical parameter of this interlaminar toughness, but also selected boundaries, yes, what we can use as allowables for a given probability of failure, 90%, 95, 99, 99.9, etc. And if we had like one scenario, normal distribution, variable distribution, we got different, of course, values. But for engineering perspective, what you will do, you will select the worst case scenario. So from here, you could say, aha, I would need to use 1.58. It would correlate with 99.9% probability of non-failure, yes. And it summarizes all our statistics here. But average here could be about 4.12, yes. So it's huge difference, yes, versus average and lowest boundary for, engineering allowable. So instead of using average here, of course, we need to use this tail value here, yes. Any questions, comments? Yes. Okay, let's go to the next example, progressive damage process, yes. And again, we published it a couple of years ago with my co-author, Dr. Kim, Dr. Clavet, Dr. Robeson, yes. So I can show it to you. So again, let me skip it. So a focus here was to see if we consider progressive damage process, what would be variation of results, yes, and have to take into account, yes. So here we have 3-point bending, as we discussed, it's linear, at some damage it starts, so became non-linear, boom, first damage, after the second damage, going here. But each line here represent different coupon, yeah? So altogether, it will show you cloud of statistical results, yes? And you see they're not too far from each other, but on the other hand, we still show quite, significant variability, yes? And here representative coupons, of course. So when we are using it, yeah, let me skip it. When we are using it for bigger population, so each individual coupon will have different patterns. Here's your coupon 1, coupon 2, different coupons, but qualitatively, they're quite similar. So if they're qualitatively similar, we can combine them for quantitative assessment of statistic and make predictions not only for average but for tails, for extreme scenarios. So usually what people do, it's very time consuming, expensive test, but it's extremely valuable. So we had about 20 different coupons, yes. Our technician tested each of them. So each line here, yes, it's individual coupon, yes. So you see cloud is relatively narrow. Yeah, it's kind of, showing qualitatively it's the same, yes. But it's provide us also with very good, opportunity to quantify variability here at the very beginning or during the process, yes. So, for example, if you want to design something, you will not select the best case. Of course, you will select the very worst case, yes? And, one of hopefully major takeaway from this class would be, for entire class, as engineers in structural analysis, always focused on the very worst case scenario, yes? You don't care if there are other locations what exceed strength, you need or toughness, you always need to worry about scenarios where you have problems, yes, and your design will be focused on those locations. So again, about 20 different coupons, all of them are about the same, qualitatively the same. So we can quantify them, and this is analytical methods have to do it. Let me skip it, yes. But bottom line, test validation. So this is similar diagram what we predicted because we were interested at the beginning. So this distribution, blue line, it's test. Black and the green lines are two different variants of analytical predictions, and gap between them, it's about 10%. So for absolutely blind, completely independent predictions, yes, it's considered to be very, very, very good because usually we have much bigger gap, like at least 20%, etc. So we're extremely pleased, yes. But this again, example, coming back, half, toughness, it's characterized, yes, at coupon level, especially if we need to know what is the level of their statistical variability. Yes, what's the level of their statistical variability? Any questions, comments so far? It was this example of progressive damage. Let's go to this full-scale in situ characterization. Let me get in situ, it's from Latin. Should be like in this form, yes. So what in situ mean? What in situ mean? So you have structure, actual structure, not coupon structure. You test it for some load conditions, see when structure is break, and from here you recalculate material properties, yes. Usually people go in opposite direction, like direct approach, or it's to have material properties from coupons and predict how structure behave, yes. But for some cases, it's very convenient to do exactly opposite, specifically generate some structures, break them, and from here recalculate material properties. And I will show you one example in this direction, yes. So again, it was work we published a couple of years ago with my co-authors here, yes. And statement of the problem was the following. Statement of the problem was the following. We had very thick tubes, very thick composite tubes. You see, those are orientational fibers, yes. But we needed properties of those materials, primarily interlaminar, yes. And for interlaminar, as I showed you before, usually people use these 3-point bending coupons, yes. But here it was very difficult to generate 3-point bending coupons, as I showed here, yes, because you have curvature in one direction. So if you cut coupon, it will not be rectangular, yes, it go like with this curvature, yes. And because it's so thick, actually it's very hard to generate this type of quasi beam coupon. So we started to think, okay, so what to do? And actually it's quite typical situation. Then existing standards will not cover your needs. So what to do in this situation? You or your colleagues need to propose new tests. Yes, and excuse me. And this is exactly what we did. So we said, okay, what would be test to measure interlaminar damage? And first of all, initiation and eventually propagation. But this work is focused on strength, so damage initiation. Yes, so crack along with this direction. Yes. So we proposed actually this type of test. We could say, okay, yes, if we have this tube, yes, let's cut small ring, have one insert, another insert, with the radius here smaller than radius of inside surface, and apply load in both directions, like tension load, yes? So this guy go up, this guy will go down, and because of that, entire ring start to bend. So this is a new test we proposed, and the logic was because of bending it's shown here, because it's a curved shape, and moment is non-uniform, of course, because moment here would be zero, moment here would be zero, and it will be non-uniform distribute. And because non-uniformity of moment, we could expect shear components, and because of shear components of force, we could expect internally shear stresses and shear strain, yes? So this was the idea to mitigate this challenge of thickness and strength, and instead of doing this more or less standard test or modified standard test, to propose completely different test, yes? And we used actual tubes, so results should be very close to real data, yes, what you have for the same structure, yes. And why you call in situ? Because we're applying it to actual structure, yes. It's not for simplified coupons, but for actual tube, yes. Let me show you a little bit. So this is how it's deformed. So you see, instead of original circular cross-section, after deformation, it's became ellipsoidal because there will be elongation here and here. But also we see those interlaminar cracks, what we really wanted to capture, yes? So ladies and gentlemen, it's a very important point how experimental testing is performed, because when you design structure, yes, you really want to avoid damage, yes, because otherwise it will be a bad scenario. But when you propose experimental test to capture, strength property, you really need to generate damage, because based on this damage, you could say, from here I could capture allowables or strength or toughness, for example, yes? So this was a point to prove that we really have interlaminar damages along, boundary between different layers, yes? Boundaries between different layers, but also, with experiment, trust but verified, we apply computed tomography, and of course we saw, our cracks also along those boundaries between different layers. Always check and recheck, yes? So this is DIC, digital image correlation technique, as we discussed before, but applied to this structure, yes? So this is scenario when we apply load for strain epsilon some XX in this orientation, in this orientation, yes? And this is just before damage. So you increase load. So here you would see strain concentration because it's symmetric here, 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 and here. And of course, you could ask me why strain here and here are not the same, or strain here and here are not the same. Answer is simple, yes, statistical variation, yes. Even absolutely symmetric structure will not have exactly left and right or top and bottom, to a slight variation between them, yes. We cannot avoid it, yes. And here, of course, you see here was a little bit higher, but for another coupon could be opposite, could be left side or top side versus this bottom, yes. But for these coupons, we had right bottom corner, the weakest one, increased level of load. You see it became, brighter, so strain increasing, boom, at some level, we will see crack, and crack will propagate, of course, along interface between those different layers. Exactly what we wanted, yes? But here you see experimentally, how it's predicted. And now, because this guy cannot handle strain, now opposite side became brighter, so now strains here increase, yes? But now, again, increase here, you increase level of load, now you have the second crack, now you have crack here, and eventually you will create network of cracks, yes? So this image, it's 100% set of images. It's 100% experimental, and it shows actually how you can, visualize process of strain distribution and expected damage, yes? So what we also did, of course, this would be for another strain in YY. Again, at the very beginning, this is the weakest guy. Increased level of load became bigger. And now, boom, it's scenario of the first crack, experimental you see, and eventually it's create this network of interlaminar interfacial cracks, yes. So this is how test will look like, force versus displacements. Again, it go linear, boom, it's damage. After that, reduce stiffness, continue to grow, boom, another damage, and eventually it will be this process, yes? And this was scenario when I had one type of insert, and this was another scenario when insert was with large radius. To be sure, we don't have bending, but we have primarily tension at ends, yes, left and right ends, yes. And this is a corresponding finite element prediction of expected shear components. So now I can consider 1/4 to do analytical. This is 100% analytical prediction. So for a second, remember this distribution, and let's go to this distribution. It's rotated like opposite, but it's exactly what we see here, yes, almost like twins, yes. So we were extremely pleased to be sure that our predictions are practically the same as our, independently measured distribution of strains, yes. So what we did here, predicted this strain analytically, compare with experimental results, and by comparison, maximum strain here versus maximum strain measured, you can calculate allowables, actual allowables in this case, interfacial allowables. So this is diagram, reaction versus displacement, finite element. This is reaction versus displacement by test. Here I don't know stiffness, but I can correlate, and comparing this point to this point to predict stiffness, but also predict strength, interlaminar strength. Stiffness is predicted by comparison this slope with that slope, yes? And strength, I believe, was the next slide. Yeah, we can compare this point, this point, and it will receive interlaminar shear strength. Yes. So this was example coming back to this statement. What to do with material characterization if you don't have appropriate standard, or existing standard cannot be applied directly. So you need to propose non-standard test, yes, if needed, and to be sure it's capture your damage mode. In this case, it was interlaminar damage. It's shown here. Yes. Any questions, comments? Okay, very good with that. And this is another thing I wanted to share with you again. It's extremely, popular area now, very growing rapidly. Growing very quickly, rapidly, because it's based on a lot of, computational advancements. Yes, and it's called computed tomography. And I will show you a couple of examples, but many of you probably know it from medical applications. Yes, like body could go, can be tested under different angles, and you will see what is going on inside. Yes, so it's heavily used in medicine, but we are also using it for engineering applications. Now we'll show you a paper we also published recently, a couple of years ago, on, let me make it a little bit smaller. Yes. It's focused on X-ray computed tomography, because it could be not only X-ray, but MRI also based tomography, but this is X-ray based. So let's skip a few images. So how it looks like, yes. So you have a sample or structure, and you have source of X-ray, and here you have screen, yes, digital detector. In old times, it used to be films. Now it's, of course, everything is digital. So what you do, yes, you apply X-ray, so you will receive image here. After that, you rotate it under some angle, again apply it, X-ray, and you will have another image. So you can do it many times under different angles, go 360 degrees around. Depending on accuracy, you can use every 1 degree or every 2 degree or every 1/10 degree. It's depending how much accuracy you want to capture. But bottom line, you will receive population of images under different angles. Yes, something like that. Yes, something like that, but under different angles. So after that, advanced programs will reconstruct you 3D image, what is going on inside. This is the reason it's called 3D X-ray computed tomography. Yes. So key would be 3D. Eventually, it's create almost like volumetric. You can rotate it digital and see what is going on inside. And it's computed, because it has to be computed from different positions, from using images from different positions. And actually, this computed tomography technique got Nobel Prize when it was about 30 years ago, because it was really, a game changer in medical field. And it was not only applied to X-ray, it was applied for MRI, yes, based on magnetic properties of different tissues in our bodies and in different structures. So if you had MRI, you probably remember, how it looks like. You can see almost like your body became transparent. You can see what is going on inside. Yes, super impressive. It's super impressive. So not surprisingly, it's got a Nobel Prize. And actually, it was a lot of brain behind it, how to recalculate 3D, reconstruct 3D image based on family of 2D image, yes? And it was extremely complex mathematical problem, so a lot of bright people were involved in development. And it's still people continue to work in this direction to make it more accurate, and more advanced, and more advanced. So how it looks like, this is real structure, like, for example, metallic. Now you have X-ray projection under different angles, so you see family of them. After that, a program will recalculate volumetric image, and after that, actually, you can play with the different position. This is CT generate. CT is from computer tomography. CT generate image, which is practically the same as here, but with all internal design, So, for example, what we are doing with that, we are using it for analysis of composite structures and to see damage pattern, which is inside, yes? So it's not easy to go inside, yes? So this is, for example, composite structure with 33 different layers. Why some of them are gray and other are almost white? Because different orientation. This is cross-section. So here you have more fibers, here you have less fibers. So this is difference in color slightly. But the coupon was like that. We have rectangular coupon with hole. We applied twist, and we wanted to analyze what will be actual process of damage here with the plan to compare with predictions, yes? But for this type of structure, it's not easy to see damage because damage actually initiate inside, yes, especially at the interfaces of between this hole and entire body, yes. So this was the reason we were extremely interested to apply this X-ray. So this is how it, let me move here first. Yeah, so this is how CT images will look like. This is load step 1 here. This is load step 3, load step 5, increase level of load, yes? And those white are, light kind of domain. That's generated damages, actual damages during the test, yes? But because CT produce three-dimensional view, you can see from different angles. So this is front view, but if I rotate it slightly, this is how, damage accumulation would look like under certain angle. And of course, inside damages would be impossible to see otherwise, yes? Now I increase level of load. This is front view. It's what we call like butterfly type of damages, yes? And this would be, view of actual damage inside of the specimen, but rotated under certain angle. And this is close to complete collapse. We increase level dramatically. So again, it's front view of damage. It's still inside, but view from front. So this is view of damage under angle, yes, under different angles, yes. And what we did here, if you're interested, we created like this type of rig. This is this coupon with hole to install it here, applied torque. So what we did actually, we applied CT, after that increased level of load, made new CT, again increased level of load, made new CT, etc. So for each level of load, we could see pattern of damage, internal damage, which is critical important, yes? So it's generated for us almost animation of the process of damage as a three-dimensional view, yes? With two-dimensional, it's easy. You just put external, yes? You put camera and you see what is going on. But 3D internal, this was extremely interesting test. And we actually, created, and now you see different patterns of damage inside, but also it was point to see how damage changes a function of load, yes? So this is torque, this is angle, you increase, go, boom, collapse. But here you will see accumulation of damage in this domain. And we played, you see, one level of, one family of curves, another, because we played with different coupons. One was 33 layers, another was 55, very thick, relatively thick. So, in both cases, we saw it's extremely good method to do it. And this is like for some specific cross-section. This was cross-section here. If you see, let me increase a little bit. Yeah. Can you see it here? Yes, so this is hole, this is specimen. So we cut here, we see cross-section with the different increments of load, became more and more damages. So nothing here unloaded. This is load step 1, first crack. After it start to propagate. Step 3 became more and more damages, 4 more and more, and load 5, you see a lot of damages, including almost like catastrophic damage in this domain. Yes, this is another cross section here, similar way. At the very beginning, 1 crack became bigger, became 2 cracks, longer cracks. Eventually, it's propagated. It's kind of progressive damage. And again, we proved that key situation hits interlaminar damage risk. Yes. So idea was, how to improve the structure. It's to focus on interlaminar damage. And actually, it was optimization recommendation here. Yes. This I showed you already. It's how to play with 3D. It's almost like if it would be glass structure, so you can see through. But it's not glass, it's actually black, yes? It's like carbon fiber. It's like completely non-transparent, but through this CT, you can see a lot of stuff inside, yes? And those are details how we did the test to be sure it's kind of can be, torque can be applied with specified angle, and those are different levels of load, different patterns of damage. So almost like if you see through body, through structure, what is going on. And those are a few images when it's collapsed, how internally pattern of fibers looks like. So one of observation was we actually saw that fibers themselves also will be broken after interlaminar damage. So again, we propose several recommendations to improve structural performance of this type of stuff.